In this video, I want to go over the Bergeron process or cold cloud process for generating raindrops from water droplets. The Bergeron process is the main process by which raindrops are made, and so it's the dominant process that creates precipitation on Earth, so it's important to understand how it works. So here I have a cross-section of the Earth, and I've also shown the 0 degrees isotherm. So this is the elevation above which temperatures are below zero. We know that it gets colder as we go up due to adiabatic cooling. And the Bergeron process starts with the generation of water droplets due to some ascending air. So I've got ascending air rising like this. And as it ascends, as you know, it will reach saturation and begin to form water droplets. These are the little water droplets forming here. And these water droplets are now going to be carried further past the 0 degree isotherm up into the sub-zero portion of the atmosphere. So these are high clouds usually, where the temperatures are very low. Now you might think that at this temperature, these water droplets would spontaneously convert to ice crystals, but that doesn't happen. That's a really difficult process, as I'll explain later. So they exist in this supercooled state as water droplets below 0 degrees. In fact, it takes a temperature of about -40 degrees to actually make these things spontaneously transform into ice. So in the upper atmosphere, we have these supercooled water droplets. In addition, assuming that there are some kind of ice nuclei available. These are sort of different than water droplet nuclei. They have to be sort of materials with a certain kind of structure that will allow ice to form on them. So they're much rarer than cloud condensation nuclei. But assuming that such nuclei exist, and usually a few of them do, we will have a few, not very many, but a few ice crystals that form directly from water vapor in the upper atmosphere around these ice nuclei. So again, there aren't as many ice nuclei, so there are far more water droplets, supercooled water droplets present in the upper atmosphere than ice crystals. So we have this situation in the upper atmosphere where we have simultaneously in the same location, we have small water droplets, a whole lot of them, and a few ice crystals, a few of them. And this is what is going to lead to the Bergeron process. So the first thing I want to talk about is the ease of transitions between these different states. So we have water vapor, this is supposed to be water here, and we have ice. And the transitions between those are not all easy. In fact, some of them are really hard. I already talked about this, that direct conversion of water to ice, this is extremely hard. It takes temperatures that are very, very low to make this happen spontaneously. On the other hand, you already know that transitions going from a more structured phase to a less structured phase, for example, ice to water and then water to water vapor, these are relatively easy. Evaporation is easy and melting is easy. One additional key point here is that if an ice crystal already exists, if we have an ice crystal existing, then the transformation from water vapor to ice is relatively easy. So this path here is relatively easy if the crystals already exist. And we're going to take advantage of this again in the Bergeron process. So in a nutshell, what the Bergeron process actually does is it allows us to circumvent this difficult process of going from water to ice by going through water vapor. So we're going to show by the Bergeron process how we can go from water to water vapor and then water vapor to ice and make ice crystals. And the ice crystals, as we'll explain, will then transform back to water, creating raindrops. The key thing that makes the Bergeron process work is the different water vapor pressures around at equilibrium surrounding a droplet of water shown on the left and a crystal of ice shown on the right. So if I indicate the concentration of water vapor or the water vapor pressure, the darker gray in the environment, the atmosphere surrounding the water droplet indicates that this is a higher water vapor pressure or a higher concentration of water in the atmosphere than at equilibrium surrounding the ice crystal. There's simply more water vapor at equilibrium surrounding a water droplet than there is surrounding an ice crystal. If the water vapor concentration around, let's say, a water droplet is not the equilibrium concentration, something will happen. So here we show at the top what it should look like at equilibrium. If we have too little water vapor pressure, too little water vapor, and too low a water vapor pressure in the surrounding air, then what will happen is the water will evaporate, transferring water from the liquid water into the atmosphere. And as that happens, the water droplet will get smaller and the air will get more enriched in water vapor until we reach equilibrium. If the water vapor pressure or concentration of water vapor in the surrounding air is higher than equilibrium, if it's oversaturated, then in theory, if it can, water will precipitate onto the water droplet, taking water vapor out of the atmosphere and transferring it to the water droplet, which makes the water droplet bigger and the concentration of water vapor in the air smaller until, once again, we reach equilibrium. Now, the thing about water vapor pressure is it's a pressure. And if we have existing in the same place higher concentrations of water vapor pressure surrounding a water molecule and lower concentrations of water vapor pressure surrounding an ice crystal, water vapor is going to flow from high pressure to low pressure. So there will be a movement of water vapor away from the water droplets surrounding the water droplets to the environment surrounding the ice crystals. In a sense, what happens is the water vapor, if we have a mixed environment of both water droplets and ice crystals, in a sense, what happens is the water vapor surrounding all of them achieves some kind of middle value, something less than the saturation water vapor pressure surrounding a water droplet and greater than the saturation water vapor pressure surrounding an ice crystal, something in between. And that water vapor concentration is unstable for both of these phases. It's undersaturated with respect to the water droplet and oversaturated with respect to the ice crystal. So in this environment, the water droplets are going to continue to evaporate while simultaneously the ice crystals are going to continue to grow until all of the water has been transferred from the water droplets to the ice crystals, and the ice crystals have grown really large. So if we go back to our first diagram, we've gone from the situation on the left where we have a mix of lots and lots of tiny water droplets and a few small ice crystals to a situation where we have a few giant ice crystals. All of the water has turned into ice. These ice crystals are now really large and they can fall rapidly to the ground because they're large. They have a high settling velocity. And as these ice crystals fall to the ground, one of two things can happen. Most commonly what happens is they transform into water droplets, big old fat raindrops, I should say, as they move through the warmer part of the atmosphere, because once again, the transition from ice to water is a relatively easy one to happen, and we get rain. Sometimes, however, we get these large ice crystals. Maybe they're so large. Now let's make a giant one over here. This is a giant ice crystal. It actually manages to fall all the way to the ground and hit the ground as an ice crystal. And we call that, of course, hail. So generally, when we see hail, it must be coming from a Bergeron process because the process is one which produces ice first, and then as the ice falls to the atmosphere, it will become rain. A typical thunderstorm, the rain in a typical thunderstorm is formed by the Bergeron process, which is why it's not surprising that sometimes thunderstorms bring hail. So this is, in a nutshell, how the Bergeron process works.